Hey geometry friends, here we are in section 3.5, and today we're going to work on proving lines parallel. So we're going to start off this chapter not with some vocabulary, but with some new postulates and some new concepts. So here's the first one, postulate 3.4, converse of the corresponding angle postulate. So you remember, this is kind of a little bit of a thought bubble. We had this concept that if lines are parallel and they're in a plane and they're cut by a transversal, I didn't write all that out here, but if lines are parallel and they're in a plane and cut by a transversal, then the corresponding angles are congruent. You remember that? Well, right now, hopefully you do. And right now what we're going to talk about is the converse of that, right? You remember when we talked about converse is when you take the hypothesis and conclusion and you switch them. That's what we're going to do. So now, if two lines are cut by a transversal so that the corresponding angles are congruent, then those lines are parallel. Remember, we started off with a parallel line cut by transversals. Now we're starting off with just random lines cut by a transversal, but we know that the corresponding angles are congruent. Then the lines are therefore parallel. So this is one way of proving lines parallel. Well, I should say another tool for, or a tool for showing that lines are parallel. Realize that this is a postulate. This is something we're holding on to as fact. We're not going to prove it. Let's go on to some other concepts that will help us prove lines parallel. Here's another postulate called the parallel postulate. It states that if given a line and a point not on the line, then there exists exactly one line through the point that is parallel to the given line. So you're given a line and some random point not on the line. This postulate assures us the fact that there exists some other line that I could draw that will go through that point that is parallel to the line we started off with. Seems reasonable. Let's go on to some theorems. So here's another theorem. Well, here is it, the first theorem that we talk about, alternate interior converse. Let's read them actually. The consecutive interior angle converse, alternate interior, I said X interior here, but this should have been X, I should have said exterior. So alternate interior angles converse and perpendicular transversal converse. These first three, remind me so much of the postulate that we just did, the first postulate that we talked about today. So realize that in each of these, we're going to start off with parallel lines. No, we're going to start off with lines cut by a transversal. And in this case, the alternate exterior angles are going to be congruent. That's going to imply parallel lines. Here we have two random lines cut by a transversal, and then we're going to see that the consecutive interior angles are supplementary. If that's true, then we've got parallel lines. Over here, the hypothesis is going to be if you have two random lines that are cut by a transversal so that the alternate interior angles are congruent, again, we got parallel lines. So these three are direct converses to what we already know. Let's take a look at this one. This is also supposed to be a converse. Let's see. In a plane, if two lines are perpendicular to the same line, then they are parallel. So this is converse to the perpendicular transversal theorem that we had before. So you can see that these are really like, I kind of think of it as the other postulates and theorems that we're talking about went in this direction. These guys are going in the opposite direction. All right, so they shouldn't be too hard to remember. So let's take a look at example 1. We're going to identify parallel lines. Given the following information, determine which lines, if any, are parallel. State the postulate or theorem that justifies your answer. All right, so let's take a look. Let me highlight the angles that they're giving us. They tell us that angle 1 and angle 6 are congruent. So here's angle 1 and here's angle 6. When I look at angle 1 and angle 6, I can see that P is the transversal, right? And the two lines that are created, or that also are needed to create those two angles, would be these guys, L and N. And so these 1 and 6 are alternate exterior angles, and therefore L and N are parallel. So I'm going to write L, I'm going to use a pen. I'm going to write L is parallel to N, and that's by, do you remember the, I think this is the theorem, this is the alternate exterior angle converse theorem, something, and basically it's like this. Two lines in a plane cut by transversal form congruent alternate exterior angles, then the lines are parallel. So this is kind of a you know, I don't know, I don't want to say properly abbreviated, but it's an abbreviation basically of the theorem that we need here. So let's look at this next guy. So we're talking about angles 2 and angle 3. So I'm going to highlight those first, clearing up what we just did for the last problem. So here's 2 and here's 3. And you can see 2 and 3 are both recognize that P is the transversal, and the lines that are also needed to create angles 2 and 3 along with the transversal would be these two. So we're talking about lines L and M. And L, let's get L here. L is parallel to M, and that is true because these are alternate interior angles, so two lines in plane cut by transversal, and they form congruent alternate interior angles, right? Alternate interior angles. If this is the case, then the lines are parallel. All right, and that's it for example 1. Let's take a look at example 2. So in this case, it says find the measure of MRQ, that's this angle here, find the measure of MRQ so that A is parallel to B. So I want these two lines parallel, and I want to figure out what MRQ must be and show your work. Well, MRQ, I know I can tell that that angle there, let's see if we can give some, that angle here, and this is some other information we have, this angle here, they're alternate interior angles. And we know that alternate interior angles are supposed to be congruent if the lines are parallel. So we need to make sure that the measurements are set equal to one another. So I'm going to set this angle equal to this one because that's what's going to ensure that I have parallel lines. And then what I'll do is I'll solve for X and figure out what MRQ is. So doing this as you guys are very comfortable with, we're going to move the 5X over to both sides. Subtracting it, we're left with 7 is equal to 2X minus 21. Add 21 to both sides because I'm going to, change the sign, blah, blah, blah. I get that 2x is equal to 28. That makes sense. Then I'm going to divide both sides by 2, and I get that x is equal to 14. All right, so with that in mind, I'm not done. I want to be done, but they did not ask me to find the value of x. They said, find the measurement of MRQ. So if I'm going to do that, I know that MRQ, which is an angle, the measurement has to be 5 times 14 plus 7. So 5 times 14 is 70, plus 7 is 77 degrees. So as long as this is 77 degrees, then these guys are equal, and then we have parallel lines. Okay, this is the last of our examples for today. So let's take a look. Home furnishing. In the ladder shown, each rung is perpendicular to the two rails. Boom, 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 boom. Is it possible to prove that the two rails are parallel and that all of the rungs are also parallel? So we need to prove that the two rails are parallel and that the rungs are also parallel to each other. Well, seeing these 90-degree angles, right? And then if you can explain how, if not, you can explain why not. Seeing that these lines that form right angles, 90 degrees, are perpendicular, it makes me think about the one theorem that we had. So I'm going to go back up and take a look at the perpendicular transversal converse. So in a plane, if two lines are perpendicular to the same line, then they are parallel. So I think this is what we would be using. In a plane, if two lines are perpendicular to the same line, then they are parallel. So let's go back. I'm going to hold on to that, and let's go back to our question. And so now that we've got this idea in a plane of two lines in a plane, so let's consider the plane of the ladder. In a plane, if two lines are perpendicular to the same line, we could use the first rung, then those two lines are parallel. So I think that's a pretty straightforward way of proving that the two railings are parallel. Then the question is it possible to prove that all of the rungs, these guys, are parallel as well? And I think that the answer is clearly yes, because if the railings are parallel and this is perpendicular to this, then here is a line that is perpendicular to two lines, then these two are parallel. And I can continue that argument and say, well, this is perpendicular, this is perpendicular. You know what I'm saying? Are you with me? So the answer is yes, and the explanation was a little bit garbled there, but the key to that explanation would be this guy here. And with that in mind, this is the end of our lesson. I look forward to seeing you guys soon. Take care and let me know if you have any questions. Have a good one now.